Good day, everyone. In this presentation, we will learn about static equilibrium, the balance of forces and torques. What is static equilibrium? The static equilibrium is a physical state in which an object is at rest with no net force and no net torque acting on it. Thus, for static equilibrium, the object must be in translational equilibrium as well as in rotational equilibrium, and another vital condition is that the object must be at rest. Static means not moving, stationary, or at rest. Equilibrium means balanced forces equals constant velocity.
Condition for static equilibrium. First, the object must be in translational equilibrium. It means that the net force acting on an object must be equal to zero. Summation of force is equals to zero, where summation of force is the vector summation of all the forces acting on the object. Second, the object must be in rotational equilibrium. It means that the net torque acting on the object must be equal to zero. Summation of torque is equals to zero.
The third one, the object must be at rest. The object under static equilibrium must be in a resting condition and it should not move or tilt. Thus, the object must have zero angular velocity and zero translational velocity. Velocity equals zero and work equals zero.
Example, torque balance, where the net torque of the system is zero. A torque balance consists of a rigid beam that can rotate about a fixed pivot point and masses that can be attached to the beam different distances from the pivot. The masses exert torques on the beam which depend on the magnitude of the force due to the gravity, the distance from the pivot, and the angle between the force and the beam.
Application in everyday life. First, a book resting on a table. The force of gravity pulls the book downwards while the table exerts an equal and opposite force, known as the normal force, pushing the book upwards. These two forces balance each other, resulting in static equilibrium. Second, a ladder leaning against a wall. The weight of the ladder creates a downward force, while the wool exerts an equal and opposite force, called the normal force, pushing the ladder upwards. Additionally, the friction between the ladder and the ground prevents it from sliding. All these forces work together to maintain static equilibrium.
And lastly, a person standing still. When a person is standing still, the forces acting on them are balanced, resulting in static equilibrium. The weight of the person is balanced by the normal force exerted by the ground, while the force of gravity pulling the person downwards is balanced by the force of the ground pushing upwards.
In static equilibrium, there are two things that you need to know. The net force must be zero. The sum of all forces in the x and y direction must be equal to zero, so you have translational equilibrium. Now, you must also have rotational equilibrium, so the sum of all the torques must be equal to zero as well. When these two conditions are met, static equilibrium will occur.
Challenges and problem solving. Now, let's review torques. Let's say if you have an object that can rotate about this pivot point, and if we apply a force at an angle, and let's say this is the left of the bar, then the torque is the product of r and f, which is f times r sin theta, where theta is the angle between r and f. So we're going to use this formula to calculate the torque in this problem. In addition, we need to talk about the sign convention step we're going to use for our torque calculation. Let's say if we have two forces, F1 and F2, F2 will create a counterclockwise rotation, so it's going to create a positive torque. F1 will create a clockwise rotation, so it's going to create a negative torque. Let's try this problem. A 40 kilograms child sits in a seesaw 3 meters away from the pivot point. The mass of the bar is 10 kilograms. Where should a 30 kilograms child sit to balance the seesaw? What is the normal force exerted by the pivot point? So let's begin by drawing a free body diagram. So here's the pivot point, and here's the first child. Let's just draw a stick figure. Now the weight force exerted by the first child, let's call it F1. And this child is 3 meters away from the pivot point. Now the second child is X meter away from the pivot point, that's what we're looking for. And this child will exert a weight force that we're gonna call F2. Now, the mass of the bar also exerts a weight force, and the pivot point exerts an upward normal force, which supports the other three downward forces. So we can calculate the normal force first, or the location where the 30 kilograms child sits. So let's start with the normal force. We know that the sum of all forces in the y direction must be equal to 0 if we are to have static equilibrium. Now, the normal force is an upward force, and the other three forces are downward forces. So we're gonna put a negative sign in front of it. Now, if we add the three forces with a negative sign and move it to the left side of the equation, we can see that F1 plus F2 plus the weight force of the bar is equal to the normal force exerted by the pivot point. So the weight force of the first child is simply mg. It's 40 kilograms times 9.8. The weight force of the second child is 30 kilograms times 9.8, and the weight force of the bar is 10 kilograms times 9.8, and it should equal the normal force exerted by the pivot point. And therefore, the normal force exerted by the pivot point is 784 newtons. Now that we have the normal force, let's calculate the location where the 30 kilograms child should sit. Now, we need to analyze the torques created in the situation. The normal force and the weight force will not create the torque because they are located at the pivot point. They're all value of 0. Torque is F times R. So, if you're directly on a pivot point, that force will not create any torques. So there's gonna be two torques created. T1, which is a counterclockwise torque, that's positive. And T2, that's a clockwise torque, so that's gonna be negative. We know that the sum of torques must add up to 0, so that's T1 minus T2. If we add T2 to the other side, we could see that T2 is equal to T1. 2 is F2 times R2, that's X times F2. And torque 1 is F1 times R1. F2 is M2G, F1 is M1G. So if we divide both sides by G, we can get rid of gravitational acceleration. The mass of the second child is 30 kilograms times X, and the mass of the first child is 40 kilograms times R1, which is 3. So let's divide both sides by 30. So 40 over 30, we can cancel 0. That's basically 4 over 3. So 4 times 3 divided by 3, we can cancel the 3, so therefore, X is equal to 4. So to balance the seesaw, the 30-kilogram child needs to sit 4 meters away from the pivot point.
To conclude our presentation, static equilibrium is when forces and torques on a system are zero, and it does not move or rotate. It is useful for designing and analyzing rigid structures. We have learned how to identify, analyze, and solve static equilibrium problems and examples.
And that's wrap up our presentation on static equilibrium. Remember, balance is the key to stability, both physics and life. Thank you for watching.